Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to be going over how to understand and use your K value when you have a very large K value with a shift towards the favored side. So in my previous videos I was talking about different scenarios in which K is small or K is large or K is close to Q, in which you could assume that X is going to be negligible as far as the change or the shift goes. But what about those reactions in which the shift is going to be large, so large that the reaction wants to go 100% in that direction before you equilibrate? So that's the situation which I want to go over now. In those situations, you're not going to be able to assume that X is negligible. So you'll have to do stoichiometry first. So let's get into this. So I'm going to go over two situations in this video. I'm going to go over the first situation and then that situation. In this situation, we're going to assume that large X, I'm sorry, we're going to assume that K is large. We have a very large equilibrium constant and the shift is towards the favored side. So here's my example. So I have A plus 2B is going to give me 3C plus D. And so in my concentrations, I have initial concentrations. I have 3 molar of A, 2 molar of B, 0 for C, and zero point 0.5 molar for D. Now, one of the things you want to, again, point out is that here K is very large. So again, K being large means that it's favoring products. So again, the ratio of products over reactants, that means that you have a whole lot of products at equilibrium and a very few reactants. So this equilibrium is favoring overwhelmingly the product side. Now, keep in mind, we got to figure out our Q value. Now, if we put in the values for our Q, we'll find that Q is 0, and therefore it's going to shift towards the product. So again, from 0 here, we know that it's got to shift towards product to make product. You can't have 0 product. So anytime there's a 0 on one side or the other, you know it's going to shift towards the side with the 0. And again, you can do Q value. You can figure out the Q value for that by plugging it in, and you'll see that Q is 0, which means it's going to shift towards this way. So we know it's going to shift towards the side that is favored. Now, in a previous video, we had K is large, and it was shifting away from the favored side. And we said that under that condition, you can assume that X is going to be negligible. The change is going to be very, very small. But in this case, the shift is towards the favored side. And so because the shift is towards the favored side, then you can't assume that X is negligible because it's all going to want to go this way. So you're going to have a large shift this way. And so in that case, in this sort of situation, you can't assume X is negligible. So what you need to do is you're going to have to do two steps. And the first step is to do a stoichiometry table. And what we call that stoichiometry table depends on your teacher or your professor, but I call it an ICF. You might see it as an IF table or something else, but you got to do a stoichiometry problem first and then do an ICE table. So what does that mean? Why do stoichiometry? Well, so because we know it's shifting in this direction to the favored side, we know that because of the K value, this side is going to be overwhelmingly favored compared to this side. So almost all of this is going to become product. So we're going to end up having a very, very small amount of this at equilibrium. So why not just decide that it's going to go 100% that way? So we can assume first that it's going to go all of this way 100% first, figure out what the changes are going to be, and figure out what the final amounts are going to be at the end. So we're not doing an equilibrium problem. We're not doing that. We're going to assume it all goes 100% this way first. So we got to do stoichiometry. Okay. Once we get the final amounts here, then we can use the final amounts to do an ice table. And I'll explain that in just a moment. So first thing I want to say is that when you do a stoichiometry table or an ICF table or an IF table, whenever you do stoichiometry, you want to do it in moles, not molarity. The only time you want to do it in molarity, or that you can do it in molarity, is under special circumstances where moles and molarity are going to be used in the same way. For example, if I assume, or if I'm told that I have a 1 liter amount of solution, well, 1 liter, my molarity is out of a liter, moles over liter. So if I have 3 molar solution, right, that means if I have 1 liter of solution, I have 3 moles. So if I'm told that I have 1 liter of solution, then the molarity that I'm using is the same as moles, so I can just use the same numbers. So I can just put in the molarities and just use them as moles, because if I have 1 liter of solution, the moles and the molarity are the same numbers. Okay. Or if I'm given some other situation in which I can use molarity and moles in the same way because they end up being the same number, then in that situation, I can use my molarity as moles. But if you're given, like, say, for example, if I have 2 moles of solution, if I have 2 liters of solution, then I need to use that volume of 2 liters, and I need to convert my molarities to moles first, and then use the moles in my stoichiometry table first, figure out how many moles I have left once everything has reacted completely, and then go from there. Okay, so let's go ahead and we'll say this is moles. We're going to use moles for instead of molarity, but it's the same number. So we have 1 liter of solution. So that means I have 3 moles. I have 2 moles, 0 moles, and a half a mole here. And so what I'm going to do is do the stoichiometry. So this is 0. I know it's going to shift this way. I'm going to assume that everything reacts completely. So basically, this is a linear reagent problem. So I need to figure out which one of these is going to be used up completely, because it's going to go 100% until one of these is used up. So according to the ratio, I have 1A for every 2 B's. So I need 2 B's to completely react with 1A. Here I have 3 A's, 3 moles of A. So to react completely with 3 moles of A, I need twice as much B. So I need 2 times 3 is 6. I need 6 moles of B. But I don't have 6 moles. I don't have enough moles of B to react with A. So that means I'm going to run out of B first. So B is my limiting reagent. So I'm going to lose all of my B. So I'm going to lose 2 moles of B. So that's my change. So my initial number of moles. My change here is 2. So I'm going to end up with a final amount of 0 moles of B in the end. Well, if I lose 2 moles of B, I lose half of that amount. So half of 2 is 1. So I'm going to lose 1 mole of A. So I end up with 2 moles of A left over after the reaction has been completed. So if I lose 2 moles of B, so for here, it's a 2 to 3 ratio. So losing 2 moles of B, if I lose 1 mole of here, it's 1 to 3. So this is an easier way to do it. So if I lose 1 mole here, then I'm going to gain 3 moles here because the 1 to 3 ratio. So I'm going to gain 3 moles of C. And again, if I lose 1 mole of A, it's a 1-to-1 ratio here. So losing a mole of here would be the same as gaining a mole here. So I gain 1 mole here. And so the final amount I gain here, that I'm going to have 3 moles of C finally. And I'm going to have 1.5 moles of D. And so that, ladies and gentlemen, is how you do your stoichiometry table. I've assumed that it's going to react completely going in this direction. I figure out what my limiting reagent is, and then that's going to determine my change. So I'm going to know I'm going to lose all of this B, so that's going to go to 0. So since I know the amount of change here, I can use that to figure the amount of change here and here. And then I add that or subtract that to get my final mole amount. So that's the first part. Once you do your stoichiometry and figure out the number of moles, now you can use this final amounts to use as your initial amounts in your ICE table. So the next thing you're going to do is you do an ICE table. Now, before you do the ICE table, notice this is in moles. You need to convert the moles back to molarities. You can't use moles in an ICE table. You have to go to molarity. But for this problem, where we assume that we have 1 liter of our solution, so dividing these by 1 liter each gives me the same numbers. In your problem, you might have 2 liters, you might have 1.5 liters, 3 liters of solution, or whatever the volume is. You need to divide the moles here by the given volume in liters, so that way you can use those molarities as concentrations in your ICE table. Sorry about that. Okay, so I divide this by 1 liter, 1 liter, 1 liter, 1 liter. I get the same numbers. So now I have 2 molar for my A, and I have 0 here for my B. I have 3 molar here, and I have 1.5 molar there. Now look at the situation I have. Now I have 0 as for one of my reactants. So since I have 0 for one of my reactants in concentration, I know that it's got to go this way. It's going to shift towards the reactants. And I know that because this is a large K value, it doesn't favor the reactants. It favors products. So I know that it's going to be a teeny tiny shift this way. So now I can neglect my X. I can assume that X is going to be so small that I can ignore it when I'm doing my ICE table. So that is why you want to do your stoichiometry first. So under this condition, when you have a large K value and the shift is towards the favored side, you got to do the stoichiometry first, figure out your limiting reagent, figure out the change, figure out what your final moles are going to be when you assume that it goes 100% in the favored direction. Once you do that, you figure out what your new molarities are, and then you do your ICE table with the shift going in the opposite direction. So here, I know since it's going to be shifting this way, then I know that I'm going to get a plus X amount of A. I'm going to get a plus 2X amount of B, I'm going to lose a 3x amount of C, and I'm going to lose an x amount of D. And so I add those together, I get my 2 plus x for A. I get my 2x for B. I get my 3 minus 3x for C, and I get my 1.5 minus x for D. So now I have my equilibrium expressions. So now I can plug those into my K. So KEQ is equal to the concentration of D multiplied by the concentration of C raised to the third power over the concentration of B raised to the second power multiplied by the concentration of A. So now I have my K expression. I'm going to plug in my equilibrium expressions in terms of X. So now D is 1.5 minus X multiplied by C, which is 3.3x or 3 minus 3x cubed over B, which is going to be 2x squared, and multiplied by A, which is 2 plus x. Okay, now, because I know x is going to be very small in shifting this direction, I can use the x is negligible assumption, and I can assume that x is going to be small for this, this, and this. Now notice the initial concentrations are relatively large, 1.532, so x is negligible is a safe bet. So I can eliminate x here, x here, x here. So now this has become a very simplified problem. Now, the one thing I want to point out is if I didn't do my stoichiometry first and I tried to do this problem using an ice table first, I would have gotten a very ugly expression pretty much like this, but I wouldn't be able to eliminate x. And I would have a very ugly like x to the third or x to the fourth power, right? And that would not work. So I have an x to the third here. I would multiply by this. I'd end up with an x to the fourth power, and you couldn't solve it very easily. If you do the stoichiometry first, and then you do your ice table, now you can eliminate x and simplify the calculation. So if you ever run into a problem where you end up with an x to the fourth or x to the third, double check to make sure maybe you need to do a stoichiometry table first and then do your ice table. So now I have a very simplified version. So this is going to be equal to 1.5. So I'm going to have 1.5 times 3 to the third, which is going to be 3 to the third. So let's put that there. 3 to the third. I believe that's 108 if I remember correctly. But we'll calculate it out later. And then this is going to end up being 2 to the x squared is 4x squared. So that's going to be 4x squared multiplied by 2. Okay, so very simplified. So now you could solve for x. This is going to be equal to KQ, which is 1 times 10 to the power of 15. Okay, so we could simplify this even more. So we can multiply these together, divide by 2, divide by 4. So we could fix that. So if we get our calculator, let me calculate this. Okay, So when I simplify this, this ends up being, I'll write it over here to give myself some room. So this ends up being 5.0625 over x squared is equal to 1 times 10 to the 15. So you can easily solve for x squared. Find x. When you do that, you get x is equal to, what is x equal to? 7.1 times 10 to the negative 8. So 7.1 times 10 to the negative 8 molar. Okay, so there you can see that x is actually very small, right? So now we can do the 5% rule, but we can see that this is very, very small compared to our original concentration. So 3, 1.5, 3, 2. So which one would be the least one? So 1.5 would be the one to check because that's the smallest one. It's the least likely to pass the test, but we'll see that it will pass the test, so it will be valid. So if we do that, let me see here. You almost don't have to do this because this is so small. You know it's going to be a percentage much less than 1. So we'll forego that. If you want to test it yourself, you can just take the x value here, divide it by 1.5 here, and multiply by 100, and you'll know that it's much less than 5%. So now, since we know that this is our x value, we can plug the x value into our expressions here and find the concentrations at equilibrium. And that, ladies and gentlemen, is how you deal with a problem where K is large and it's shifting towards the favored side. In my next video, I'll talk about what do you do when K is very, very small and it's shifting towards the favored side. Well, even in that case as well, you have to do a stoichiometry table followed by an ICE table. So stay tuned for that. Thank you for joining me. If you like this video, if this was very insightful, if this helped you in any way, please, by all means, like the video. Hit that like button. Also, share the video with your friends. Let them know about it. Also, make sure you subscribe to my channel. Hit that notification bell and click all so you can be notified by all the videos I put out. And then finally, put a comment down below. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me and have a great day.